we start our discussion of the event reconstruction in particle physics experiments, particularly at high energy physics hadron-hadron colliders. That's what we start with. And to understand what's going on, we have to go through most of the topics of the previous lectures. Without maybe you noticing it, we've been following a particle from the acceleration stages to where it collides, the particles that are produced in the collision as they travel, as they shower hadronize, as they travel through the detector, as they shower again electromagnetically or hadronically in the detector material. And from there, we have to take the last step towards reconstructing these quantities and identifying what is going on in the interesting highly energetic collision. So a reminder, what does a complex event look like? How do we think about complex proton-proton collisions? You can imagine here proton colliding with another proton at tera electron volts energies. So the proton consists of quarks and gluons sketched here, and those interact at the energy scale described, probabilistically described by the parton distribution function, which is the probability to find a given parton, which could be a quark or a gluon, inside the proton, carrying a specific momentum fraction x of the proton. That was the topic of the first lecture. So we know essentially, we've described how the proton is formed in the parton model of quarks and gluons. Now these collide in, we imagine, a highly energetic collision with a very large momentum transfer. Because the strong interaction is weak at high energies, which is a crucial feature of quantum chromodynamics that is called asymptotic freedom. The coupling constant at the momentum transfer relevant for these highly energetic events, because the coupling constant is small, the strong interaction is around 0.1. Perturbative field theoretical calculations can be carried out, and we can actually compute the quantum mechanical matrix element. It's a little bit more difficult to do that in the multi-particle field theory approach, in the quantum field theory, than it is to compute these matrix elements in single particle quantum mechanics that are ground school topic, I believe. It's more complicated technically, but conceptually it's not. One has an initial state and a final state, and one computes a perturbative transition amplitude, and that's that. So we can compute the hard parton collision in dark red here, and we can also compute the probabilities of the various decays of the particles in the standard model. So for example, we can compute, if we know the Higgs boson mass of 125.3 GeV, we can compute the probability and the angular distributions of its decay, for example, to a pair of bottom quarks, as is depicted here. We can also compute the decay of a top quark, the probability of a decay of a top quark in a bottom quark and a W, which happens to be close to 100%. So for practical purposes, the top quark always decays in a bottom quark and a W boson. And then we can also compute, at least in principle, whether we do it in practice is a different question, but we can compute in principle the probability of a quantum chromodynamics, a strong interaction Bremsstrahlung. So the emission of a highly energetic gluon, for example. This is calculable. However, in doing so, we reduce, of course, the available momentum transfer. If you have a TeV, let's say you have a 100 GeV top quark here, it travels with, it has a transverse momentum, a momentum of 100 GeV. It radiates. After the radiation, it will have less. It will have less momentum, and there's thus less momentum transfer available for the next radiation process. Because of asymptotic freedom, if you read asymptotic freedom backwards, it reads confinement at low energies, color confinement at low energies, asymptotic freedom at high energies. We believe theoretically that these are that color confinement and asymptotic freedom have the same origin. However, color confinement could not be proven rigorously yet, so there are still proofs lacking in the theoretical description of quantum chromodynamics. However, we know from all practical purposes that it is a reality. In other words, at low energy, we need to describe our bound states by colorless objects, the hadrons consisting of mesons and baryons. Why do I tell you this? Because when we follow the top quark, or for that matter, any other strongly interacting particle, it is evident that by radiating gluons and pairs of quarks, that energy is lost, and thus the strong coupling increases, which is that peculiar feature of QCD, and at some point it will diverge. In fact, at 200 MeV, the strong coupling constant goes to 1, at which value the perturbative expansion does no longer converge. And perturbative calculations are not possible. That doesn't mean that the theory collapses. It just becomes almost intractable. One has to adopt lattice simulations to compute the bound state spectra of QCD and of similar strongly interacting theories. That's why we need to stop doing calculations at a certain momentum, at a certain momentum scale, and that scale is our choice. So we compute the radiation of highly energetic quarks and gluons by means of parton showers. So we let one gluon shower, then let's say here the energy reduces a little bit, it showers again. And then at a certain momentum scale, we have to stop and say, all right, this is the energy scale where we translate the gluon and quark fields into hadrons, that is mesons and baryons. So we can say, okay, there's a little bit of quark content here, there's a little bit of gluon content here. Let's make this a meson. There's much more quark content here. Let's make it a baryon. There's a strange quark here. Let's form strange baryons and B mesons if there is a B content. Is a B. So if there is there a B quark, and thus we translate the simulated fields into unstable hadrons. That's what we call the parton to hadron transition. These are empirical models that one starts with certain assumptions, implements it in a computer, lets it run, and compares two data. Discrepancies will naturally occur, and then one tunes these models. So it's a little bit of black magic to perform this tuning, and it's decades worth of work to understand the shortcoming of the parton shower and the parton to hadron transitions. Once, however, we have the hadrons, it's a little bit easier because the hadron decay properties have been measured accurately and are in many cases also calculable. So once we have the hadrons, we can let the hadrons decay. The hadrons are often charged, and these charged particles will again, because there is a magnetic field present, they will emit soft photon radiation. So all these particles will still radiate. Moreover, we don't produce these hadrons in the ground state, in their ground states in many cases. So one produces in the parton to hadron transition, very often excited hadrons are produced, and those then de-excite on a short length, on a short time scale, again producing, for example, photon radiation or other radiation. Now we've gone from the hard interaction through the shower through the parton shower formation, consisting in the parton picture, comprising the emission of highly energetic gluons via the parton to hadron transition, to the hadrons, hadron decays, and radiation of hadrons. So we get an enormous amount, thousands typically, of particles from an fairly simple initial collision. So what's depicted here is two gluons producing two top quarks and a Higgs boson. It's not a simple process, but it has a few partons involved, certainly not 1,000. It's, in this case, it's 5 that are relevant. There's also a gluon radiated off from the hard scatter. Now, unfortunately, that's not even all of it. Also, the initial partons can radiate. For example, here, actually, we didn't have a gluon, we had a quark, but the quark radiated off a gluon that carried most of its momentum fractions. So in fact, it turned into a gluon, and the fermion quantum number is associated with the radiation. So most of the momentum in the process, in the hard scattering process in this event, comes from the gluon, although it was initially from the quark PDF. This initial state radiation, we call this initial state radiation, also has to be taken into account and has interesting physical effects. For the description of the event that we show here, it only complicates things because our relation from the initial proton via the partons to the hard scatter matrix element is less clear. There is radiation taking place. Then there is furthermore no guarantee that there only one interaction takes place per proton collision. So here two protons collide. We discussed the hard scatter event that's interesting in the top half of the diagram, but other interactions will typically take place. For example, there's a Z of gluons in the proton that can react, and if the energy of a secondary reaction is high enough, it will similarly produce particles that may overlap with the particles of the collision that we are interested in. That complicates things. And what we show here is a single proton-proton collision. As I've told you when we talked about the colliders, there are many, up to 20, typically 20 proton collisions happening in the same bunch crossing. So we have not just that collision, we have 20 collisions happening simultaneously in the detector, and we have to take all these particles apart, assign them to the correct hard scatter event, remove everything we're not interested in, reconstruct all the momenta, reconstruct the momenta of the quarks, the B quarks here, from the B quarks identify the Higgs boson, so that this Higgs has been, in this example, has decayed into the two B quarks, and from the moment, and then compute its momenta from the momenta of the partons that were reconstructed via the particles momenta that we found in the detector. You can imagine that this is a complex process, and I now will take you through the main steps. Second reminder, which we have to keep in mind, is what the detector can actually do. This is an overview of the CMS detector. ATLAS, in the respect we're considering here, is similar. All general purpose high energy physics experiments are similar. There are tracking devices around the collision vertex. Typically they consist of pixel and strip silicon sensors, which we've discussed at length. Then there is calorimetry. It can, ATLAS and CMS made different choices on the technology for the calorimetry, or whether to put the hadronic calorimetry outside or inside the magnet. As we've gone through when we discussed the spectrometer measurements, the choice of CMS was to have the strongest magnet possible that's still consistent with the strongest magnetic field that's still consistent with fitting the calorimetry inside. So we have the electromagnetic and the hadronic calorimetry. Then the magnet can be penetrated only by muons, but that leaves the possibility to measure the muon momentum with a very good resolution and with very good identification efficiency outside. So this scheme, this layout allows to distinguish few types of particles. We can unfortunately not go into details. We cannot discriminate the pions from hadrons. We would need a time projection chamber or something similar to do that. And then it would be difficult at the energies we're dealing with, but nevertheless, it would be doable. But the choice here is different. So we restrict ourselves to a fairly simple particle ID. Now we can identify the muons. Muons are simple because we reconstruct them in a dedicated system that cannot be reached by most of the other particles. Electrons are theoretically closely related to the muons, but experimentally they are very much different. Because they're so much lighter, they lose Bremsstrahlung photons in the magnetic field and in the volume of the tracker, and then they shower in the electromagnetic calorimeter. So they produce a track in the tracking system and a shower in the electromagnetic calorimetry. That's similar to charged hadrons. A charged hadron can do that too. It will leave a track in the tracker. It may start the shower in the electromagnetic calorimetry, but it's a strongly interacting particle. It's heavier than the electrons. It has less Brem. It will typically, it can go through the electromagnetic calorimetry. It will then shower in the hadrocalorimetry. So it leaves its energy there. But we have learned that the electromagnetic calorimeter also poses, just by means of the density of the nuclei, it also poses, it also acts as a hadron calorimeter. And in fact, it has one interaction length, around one interaction length, while the hadron calorimeter then has 25. In other words, we expect that one interaction takes place, one hadronic interaction takes place in the equal, but most of it will be in the hadron calorimetry. Then there are neutral hadrons. The neutral particles do not leave a signal in the tracker. That's what distinguishes them from the particles discussed so far. On the other hand, it's also difficult in the sense that you may just have lost the track. If you lose the electron track, you think it is a photon. And indeed, electrons and photons only differ by the presence of the track. So if something went wrong with your track reconstruction, you think an electron was a photon, and you will reconstruct completely different events. Now, a photon is not, the photon's track is not bent in the tracker, and it will shower in the electromagnetic calorimetry. So a shower signal without anything else in the electromagnetic calorimetry, in particular nothing in the hadronic calorimetry, will be identified as a photon. Neutral hadrons are the most difficult case. They are not, by definition, they are not charged, so you don't have a track. You typically do not have an interaction. You need not have an interaction in the electromagnetic calorimetry, but you only see a shower in the hadron calorimeter. Because hadron calorimeters are sampling calorimeters, typically the resolution is worse than the electromagnetic ones, and therefore neutral hadrons, think of a neutron, for example. Neutral hadrons are the most difficult to reconstruct particles. What we call a neutral hadron is just a shower in the H-cal. We have absolutely no clue about the ID. We only see hits in a detector of comparably coarse granularity. So neutral hadrons are the particles that we have the least idea about. On the other hand, they constitute a large fraction of the energy of all the particles that are produced in such collisions. They are really abundant. And these facts limit the achievable precision. Let's look again in terms of detector signatures as we've done in the past. That's something you have to be, for the exam, I will probably, one of the questions will be that I show you this diagram and you explain to me how it comes about. So what does a photon do? What does an electron do? What does a muon do? What do the charged hadrons do? And what does a neutrino do? Just so you know, and we'll spend a few minutes talking about this. It is a short summary of what I've discussed at length on the previous slide. So these are, this is the overview of the detector signatures. Let's look at event reconstruction now. Principles of event reconstructions. So once the showering particles have hit the detector cells, they produce ionization or scintillation or other signals that are recorded. The detector is read out and one obtains signals, one obtains a signal for each detection cell. Hadronic calorimetry, electromagnetic calorimetry with a finer granularity, and then hits in the tracker. You do not know whether this sequence of hits really belongs to a single particle, but it certainly looks so. If you want to discriminate all those little hits close to the beam pipe, you also have to take into account the hits elsewhere. Otherwise, you cannot tell to which particle a given hit or to which particles a given hit may correspond to. The first thing we do in event reconstruction is we reconstruct the muon candidates. I don't even show it here because it's so quote unquote simple. In practice, it's of course complicated, but conceptually, it's very simple. First, we look at whether we saw something in the muon system. Once we have something in the muon system, we can compute the track hypothesis and match with hits in the tracking detector, and these are our muon candidates. Muon reconstruction runs first because it's the least ambiguous. Now we are left with a few, hits in the rest of the detectors. The first step after muon reconstruction is to cluster these hits. That means we form clusters from neighboring cells that are consistent with what we've learned about the shower evolution in our detector. If there are cells hit that are adjacent in the detector, next side by side, we group them in a cluster of hits. Thereby, we reduce the information. We add up the energy that has been measured in the individual hits, and we call this a cluster. And we call these equal hits. There are many of them here in the open box. We group them in 3 clusters in this simple image. Similarly, and independently, we reconstruct tracks in the tracker. That is, there are highly advanced track finding algorithms in place to align the individual hits along trajectories of a given momentum. So here, our physics knowledge about the radiation of charged particles in a magnetic field enters. We fit the hypothesis of typically a charged hadron, and let the pattern matching algorithm find a solution. Of course, there will be ambiguities. A given hit may be associated to several tracks. There could be overlapping hits. At the end of that's why the tracking software is the most complex piece of the whole event reconstruction, and it takes the longest time to run. In fact, it consumes the majority of the majority of the CPU time of the event reconstruction, because we have 100 million readout channels. There's a lot of possible tracks to be reconstructed. So tracking runs, and then that stage is complete. At this second stage, the subdetectors are reconstructed individually. We form H-cal clusters, we form clusters in the electromagnetic calorimetry, and we form tracks. But the subdetectors do not yet talk to each other. Now we want to begin to identify particles. Let's start with charged hadrons. We do identify particles by first linking the hits according to certain hypotheses. The hypothesis can be the charged hadron candidate hypothesis. So you assume, for example, that the given track corresponds, that a given set of deposits corresponds to a charged hadron candidate. Practically, it is done by making coarse geometrical links. So you start with by saying, okay, I can link all these hits in this area of the event. They are close to each other. They are linked. They are probably corresponding to one or more particles. That guy over here to the right is corresponding geometrically to this track here. And then there is a track that's on its own. It does not have a calorimetry link. And that forms its own particle. And eventually, we use an algorithm to decide on which links we preserve. For example, the algorithm, which takes into account the resolution of the energy measurements in the calorimetry, the tracking resolution, the shower shape of the clusters, the proximity to the adjacent clusters. By construction, they must be separate. If they were adjacent, then if there was no empty cell in between, then those would form a single cluster. And the algorithm decides that, okay, here is a good track. There was a good track measurement. I'm certain about, I have a low uncertainty measurement on the track measurement. Let's say it is 10 GeV. And now we have a redundant calorimetry measurement. And let's say it is 8 GeV in the equal and 2 GeV in the HCal. However, these 2 GeV are less than what I saw in the cluster. The cluster had 12 GeV. So I take the 2 GeV that are missing from the 10 minus the 8 to remain. I had 12 here. That means there is 10 GeV. There is 10 GeV unaccounted for the hadron calorimetry, and I make a neutral hadron from that. That's how this so-called particle flow algorithm creates particles. So it takes these linked, energy deposits and uses resolution and energy momentum conservation and the energy momentum relation of the track with the calorimetry to form simple hypotheses. And what is unaccounted for is put into neutral particle hypotheses. A neutral hadron is essentially leftover energy in the HCal that is not accounted for by the charged energy that we measure in the tracker. The tracker will tell us if what the total, what the momentum of the charged component in our event is, because that's what it does. It measures the tracks of the charged particles, hence you have the momentum, and thus you can compute the energy. And then one measures the measured equal energy, and whatever is not accounted for becomes a neutral hadron if it was a hit in the HCal, and becomes a photon if it was a hit in the equal. Electrons are in this image, in this simplified image, a track that is consistent with a shower in the equal, where the shower energy and the track have to agree within uncertainties. If you have a 100 GeV, if you measure a 100 GeV track and you see a 95 GeV or 98 GeV shower in the equal, you can be fairly certain that there was an electron, at least as long as nothing is around. Some particles are so low in momentum that they cannot reach the calorimetry. That happens below 500 MeV or so. We call these loopers because they loop and leave the detector in the z direction. We can still measure the momentum, and we attribute the charged hadron hypothesis to them, although we have zero idea what they are, except that they do have a charge because we see the track. That's event reconstruction. That's how it works. Now we end up with a list of particles. We started with a list of hits in the detector, and we ended up with a list of particles. So the majority of the computing time at the LHC experiment is used for this slide. That's where the money goes, computing-wise. Let's see what we let's look at it from the practical perspective. The algorithm is called particle flow. It's a good thing to Google particle flow event reconstruction and to look at the plots in these papers and in the talks. One can learn a lot about the practical difficulties in reconstruction. But all you have to know to understand the rest of the lecture is repeated here. So we start with tracks, with electromagnetic equal clusters, with H-cal clusters, with muons, and we form particles. Now, the algorithm fully exploits the excellent tracking resolution and the granularity of the electromagnetic calorimetry. Typically, we assign the direction of flight in the angle. So the angular direction of flight is given by the track momentum because is given by the track measurement because that has the best resolution. As a function of the momentum, the track resolution is below 1% at the lowest energies. Photons, because they are showers in the calorimetry, have an excellent resolution of 3% over square root E. Numbers are similar for Atlas, slightly worse, but the liquid argon calorimetry is equally also has excellent performance. And neutral hadrons only have something like 100% over square root E. By combining the measurements in the optimal way, if you have a charged hadron, you take the track measurement. You really optimize the reconstruction, the resolution in the reconstructed momenta, because the H-cal energy resolution of a 100%, it is only driving the resolution in the energy of the neutral hadrons, like the neutrons, for example. So by carefully tuning the strategy of this reconstruction, we optimize what we can learn from the reconstructed events. Note please that at the TeV scale, once we leave the hundreds of GeV regime, the tracking resolution deteriorates. We know that because the relative momentum resolution of a spectrometer measurement is proportional to the momentum. So there must always be a momentum beyond which the track in the tracker is simply straight, and we can no longer measure its sagitta, and thus we can no longer measure with at least reasonable accuracy its momentum. At that point, we fully rely on the calorimeter measurement, which are thus complementary, as we've explained when we discussed calorimeter detectors. So all these general purpose detectors have complementary or benefit from complementary measurements at low energy in the tracking system and at high energy in the calorimetry, with the exception of photons, for example, that are measured with high accuracy down to low energies. Okay. Here to the right, we see an example of a jet that produces a certain number of photons, pi0 that decays to 2 photons and 2 charged pions. Here is the view in the eta phi plane, so in the angular plane, that's the projection on the calorimetry surface. We see here the simulated hits. Of course, we don't know in a real data event, we don't know that there was a pion, but when we simulate an event, we do know. So we have pions here, we have a K0 here with other pions here and a pi0 that decays to photons. And in gray, you see the hits in the electromagnetic calorimetry. So we have a tracking measurement that's not shown, and we have in this gray, with this indicated by the gray boxes, we have the shower and the deposited energy in the electromagnetic calorimetry. The electromagnetic calorimetry is shown here, so you get an idea about the excellent spatial resolution. These are small, the small 2x2 crystals. The H-cal resolution is much worse. So that is the granularity that I traverse here with the mouse. The hadronic calorimetry has a much reduced resolution. By putting these two images on top of each other, and by forming the clusters in the calorimetry and the track measurements, we perform our reconstruction. So, another way to view this, same information, but it is important because it tells you what to do. Well, it tells you what you can do. The tracker measures the transverse, its main measurement is the transverse momentum and the location of the track in the detector, which is done by fitting a track hypothesis to the hits in the pixel and the strip sensors. The electromagnetic calorimetry and the H-cal deliver individual hits in the detector cells, and those are clustered. The muon system outside of the magnet, the outermost detector for most measurements, measures, similarly, it measures hits which are fit to a track, and then the muon track from the muon system is again fit to the tracks in the tracker. So these are the algorithms and the main quantities from the different subdetectors, and the particle identification is shown in the bottom half of the diagram. So a muon will have a track in the tracker, it will not have a signal in the calorimetry, and it will of course have a track in the muon system. Of course, a muon is a minimal ionizing particle in the calorimetry. It's similar to a minimum ionizing particle in the calorimetry, so it will leave a little bit of an ionization signal in the calorimetry. That can account for like 1 GeV or so. That's small, sub%. An electron has a track in the tracker, it leaves a cluster, it showers in the equal, and then it stops. So it should not have a significant contribution in the hadronic calorimetry. And there's also, for the other particles, it's not expected that there are hits in the muon system. If you try this in practice, one has to take many more things into account. For example, charged hadrons can be so highly energetic that they also punch through the magnet and cause a few hits in the muon system. These are called punch-through hadrons, or punch-through jets. And these are indicative that we've lost a significant amount of energy in the calorimetry because some shower tail could actually penetrate. But the muon system then catches these, and the event is then, you can flag the event bad because you have a good indication that something went wrong. That's just to tell you that in practice, things are a little bit more complicated, but for our discussion, the simple picture here suffices. So charged hadrons consist of a track and the tracker. They may or may not have a deposit in the electromagnetic calorimetry, but certainly they will have a deposit in the hadronic calorimetry. A photon does not have a track, has a shower in the equal, and should not have a deposit in the hadronic calorimeter. A neutral hadron is similar, except that it showers in the H-cal. So these are the patterns, and we can, because no no signature in any of these 5 lines is identical, that is more or less this particle identification in the terms shown in the first column is what we can do. So we can do a lot with muons, very high precision, high efficiency, still with electrons, although it's a little bit difficult, it can be difficult to separate them from the charged hadrons. Only the hadronic calorimetry helps us. Then charged hadrons are, we cannot, there are many of them, we can record them with high efficiency and with good resolution in the momentum, but we cannot tell them apart. And then photon and neutral hadrons are the difficult guys that only depend on the calorimetry. So what we have to do is go from the outside in. Before we discussed what happens at the hard scatter and how the particles appear by means of parton shower, hadronization, and hadron decay. But really, we want to measure the parton momentum. For example, take this big quark. We want to measure its momentum. It's important to reconstruct the mass and the momentum of the Higgs boson. And we get a bunch of particles. So we had our detector cells, we ran a reconstruction algorithm, we get a bunch of particles, and these particles, they stem from these decaying hadrons, and there's no way we can resolve these decays with a detector of the granularity of current general purpose detectors. In other words, ATLAS and CMS can never resolve these showers. Only in the future, high granularity silicon calorimeter detectors with extremely finely segmented will get some chance of reconstructing the shower. Now, the good thing is it's not necessary. The response of the detector to the different particles is fairly similar. So if we measure all of them, and if we add them up, we get a good idea within 10% or so within a few percent actually, or so of the B quark momentum in this case. But first we have a list of particles, and we need, these are sprays of particles, and we need to correlate them to the initial parton. So we must go backwards now. In other words, we must cluster now, is again a clustering algorithm. We must cluster the particles to form a parton hypothesis. We call these sprays of particles jets, because that's what they are. We have if we go inside out, we have an initial state, well, we have at some stage of the decay chain, we have a highly energetic B quark, it radiates gluons, hadronized decay, and these form a jet of particles that go in a certain small area of the detector. Let's look at jet clustering algorithms. We go outside in now, you're given a list of particles, and you want to end up with a list of partons. First, one has to identify seeds, and then one has to devise a recursive procedure to associate the other particles until the whole event is clustered. So one looks at the particles, starts somewhere, maybe let's take the highest energetic one, and then one says, all right, here's a photon that's close by, so I merge these two because they probably have the same origin. And then one finds a way to finish this clustering process and end up with a set of jets. In other words, the particles disappear from the event description and jets replace them. It's important to control the angular distance of the clustering algorithm. A conventional delta R value for clustering particles is 0.4. It should not be much smaller, because then products of gluon radiation leave the jet cone. It should not be much larger because then jets merge in a high density environment. If you take an 0.8 jet, you would cluster the two B quarks inside a single jet. It's possible that one wants to do that deliberately, but let's discuss that later. Now we want to cluster we want to cluster the particles into individual jets. So we want to resolve two B jets, a gluon jet, one more quark jet, another B jet, and that guy here is a gluon jet, and here is a third B jet. That's as complicated as it gets. A TT Higgs event is really extremely complex, and we have 6, 7, 8 jets here that we want to reconstruct. Now, remember that from lecture 2, the delta R angular distance is boost invariant along the Z direction. That's really good news, because that means our jet clustering algorithm, whatever it is, will have the same performance whether or not the whole event is boosted along the beam direction or not. And that makes its performance uniform. But from quantum chromodynamics, we can already infer that there are other aspects of the algorithm that are important. These are technical terms. This is a story I tell you just so you know that jet clustering algorithms have been developed over at least 20 years to solve various problems at the interface of theory and experiment. One particular problem is that in quantum chromodynamics, it is very likely that the particle is emitted collinear to the initial parton's momentum. So collinear emission is something that happens with high probability, and we do not want to have the jet clustering algorithm respond differently when collinear emission has taken place. That means it's a requirement on the clustering algorithm that particles that point into the same direction are really clustered into a single jet. So if two particles point into the same direction, they must end up in the same jet. That's what's called collinear safety. You are safe from splitting up a bundle of particles into two different jets if they point into the same direction, because that's what you should not do, because it's very likely that collinear radiation has taken place. Moreover, we know that at small momentum transfer, asymptotic freedom read backwards, at small momentum transfer, radiation is very likely. In other words, soft radiation, a radiation of low energetic gluons, is something that happens that is expected to happen with exceedingly high rate in the shower development of the particles when they undergo the parton shower. And therefore, we do not want soft emission to change the outcome of the jet algorithm. For example, if we have two particles as indicated here, they should not be clustered into two jets, because a simple soft emission going in the middle here would make for a simpler hypothesis of a jet of the same cone size. Thirdly, the catchment area, which is the average area the particles span when the clustering is complete, should be a disk of radius delta r. So we want to specify a radius parameter and end up with jets of typically that size. Many jet algorithms have been proposed. When I started in 2009, a new paper came out proposing so-called anti-KT algorithm, which satisfies all the criteria above. Previous algorithms always felt would violate either collinear infrared safety or would produce highly irregular jet shapes. The anti-KT algorithm will not go into the details, of course. It's simple. So of course one has to select a cone size, let's say 0.4, and then one computes distance measures between all pairs of particles, and the distance is small if the momentum is large. So large momenta are preferred, and they are multiplied by the angular distance. If such a pair has the smallest distance among all pairs, then the momenta of these particles are merged, and one repeats the process. This process is continued until all particles are clustered. This delta R squared factor here accounts for the cone size if this minimum quantity does not produce the smallest distance when compared with the 1 over pt squared terms, then the candidate is separated out as a jet, and the process converges and lets you at some point the clustering arrives at the state where everything is clustered and the average distances are larger than 0.4, at which point this 1 over pt squared will be the smaller momenta, and at that point the set of particles that has been collected is called a jet. Maybe it's educative to look at the reference at the top here, because it discusses different jet clustering algorithms. Anti-KT is shown at the bottom right. That's an event in the rapidity and phi plane, and it produces beautifully round jet shapes. It can be proven that anti-KT is infrared and collinear safe. Before that, we had used other algorithms. Syscount was the algorithm I used first in my career. The Syscount tries to find stable particle cones, iterating a similar association procedure, but the definition is more complicated, and it sometimes introduces these irregular jet shapes. Then there's a Cambridge-Aachen algorithm, which also produces irregular jet shapes. Now, the other algorithms are not useless. They are useful. Cambridge-Aachen the anti-KT algorithm favors an early merge. That means if you have two particles of high momenta, because of this 1 over pt squared, it's the first thing that it merges. So it starts with merging the high energetic guys, and then it has a really highly energetic guy, and it merges the softer particles that were maybe radiated off. Other algorithms started the opposite way. They start by first accumulating the lower energetic particles, and at the end, they merge the higher energetic ones. This leads to more irregular jet shapes because you start with the low energetic particles and make a little bit higher energetic subjets. On the other hand, it helps you in identifying a substructure, because the last merging step in the algorithm is where maybe two highly energetic subjets are merged. For example, look at this W boson. Imagine it has a very high momentum. So we have two quarks with small angular separation leading to particles very close to each other in the detector. The anti-KT algorithm will start with the highest energetic particles and will then associate the soft stuff that's around it. So it will resolve these two jets. Other algorithms start by merging the highest energetic particles. So they may merge these two guys here, and they will thus merge particles from the two quarks. But that can be beneficial. That can be beneficial because this highly energetic merge happens in the last step, and you can then ask your jet whether its last step consisted of the merging of two large subjets. And in this way, one could recover the W boson inside the jet. All right, there was a lot of details on on jets. Let's look inside. What do different jets look like? What we call light quarks at Hadron Collider experiments are up-down, charm, and strange quarks. These produce a few neutral particles and a few charged particles that are clustered. A gluon jet is similar, but it is typically wider. The reason is that for the mathematicians among you, the reason is that the probability to radiate a low energetic parton is TF, which is Casimir operator of the strong interaction, which has a value of 4/3, so something like 1. And the invariant that governs the radiation of gluons is Ca, and that value is 3. So gluons radiate with a much higher probability than light quarks, and because that is so, and it happens it happens more with a higher probability in the initial stages of the parton shower, the gluon jet is wider. B jets and a little bit also the charm jets, they can be counted among the heavy jets. They have two properties. First of all, they are relatively slim. They produce only a few tracks because they are quarks, not gluons. But as we've discussed a few times, the B quark will hadronize into a B meson, since the bottom quark cannot change its flavor. A B meson, or in case of the charm quark, a D meson, will appear, and these have picosecond lifetimes and thus millimeter distance of flights, which can be reconstructed. So a B and a C jet may have a secondary vertex indicated here by the red dot. As I've discussed before, a W boson may, if it has high enough momentum, have substructure. So the particles it consists of appear in two groups, and specific jet clustering algorithms like Cambridge Aachen may resolve these two groups, and then you learn more about the origin of your jet. A top quark can be clustered in a single jet. A top quark will decay into a W boson, so you can have a W boson and then a B jet inside, because a top quark decays into a W in the B. So you have a displaced vertex and you have substructure. One has 3 centers with particles inside a single jet. A Higgs boson can decay into 2 B quarks. So a Higgs boson, a Higgs boson that decays can cluster in a jet with 2 secondary vertices. And all these boosted heavy resonances can be reconstructed by using machine learning techniques. I know that machine learning is, everybody knows about neural nets and machine learning, and it's a fancy topic, but that what we discuss here, that is where these algorithms were first used. So roughly, let's say 10 years ago, a large community of data scientists and physicists took on the challenge to identify heavy resonances like the WC, the top, and the Higgs inside these dense heteronic environments, and to find the top quarks in these sprays of particles. So that was one of the many origins of the machine learning revolution. Facebook was the other one. They want to sell you ads. That was the other one. Here we want to reconstruct the top quarks. And then there are pile-up jets. Sometimes you have bad luck, and you combine the particles from two different collisions, and you call that beast a jet. And in fact, it looks like a gluon jet. It just has two Hertz-scatter interactions. But if something goes wrong and you do not resolve this, then you think that was a gluon, while in fact it was something else at lower energy, but it happened to overlap. Okay, we repeat the identification of B quarks. We have discussed it before. I repeat it because it's important, because for many physical processes, for example, the ones I work on with top quarks, the B quarks play a crucial role, because the top quark will decay into a B and a W, and the B is the one that you can reconstruct. A typical jet system with a B quark is a hard scatter in the center, a primary vertex, and then two light jets here would be emitted, and then there is a displaced vertex inside the jet that is subject to the B hypothesis. What's discriminating is the impact parameter, which is the largest distance of any track orthogonal to the primary vertex. So it's this D0. That is what we have to measure with high accuracy. If this has a high significance, if we are very sure that the D0 is different from 0, then we can be pretty sure that the jet at the top right here originated from a B quark. I repeat on this slide here the numbers from the example I have given in the third lecture, which has the B hadron with 5 GeV and the beta gamma C tau of 5 millimeters. Typical numbers for these displaced vertices are 3 tracks or so. We start to work with 2 tracks. Of course, a single track does not have a vertex. We need a vertex to take a B. With 2 tracks, it starts. With 3 tracks, we can get a very high efficiency. There are various ways to do this reconstruction. What we typically do is we do all of them, and then we let the multivariate classifier decide on the eventual decision. We find an efficiency of roughly 60% at the 1% mistake rate. So if we are fine with getting it wrong in 1% of the cases, our algorithm finds 60% of the true B quarks. That's about what we have. Maybe it's 70% now. It has become a little bit better over the years because we refine our reconstruction. So it's okay to have a 60% efficiency if you have 1 B quark. But imagine you look at a process with 4 B quarks, then 60% to the 4th power, that's only, we talk about 15% and 15 to 16% of efficiency to reconstruct 4 B quarks. So 60% is okay for a single object, but it makes you blind once you have more than that. All right. We also have to remove the pileup, right? There are 10 to 40 pileup collisions at each bunch crossing, we need to remove the pileup from the event description because we're not interested in it. There's a hard scatter of an interesting event happening here that we want to reconstruct. So here we have the Higgs boson or the top quark or whatnot, but we have along the beam line 10 to 40 pileup interactions. So it is important to connect all the track measurements at vertices and reconstruct the position along the beam line, then identify the interesting guy and remove all the particles that are associated to any of the pileup vertices. That's possible as long as we have a track. If you have a pion, proton, whatever, you can remove the particle if it is associated to a vertex. But what do you do with a neutral particle? A neutral particle is, you cannot remove it because you don't have a track. You do not know where it came from. And indeed, that is the dominant contribution to the resolution in the reconstructed energy of a jet. We simply do not know whether a given photon or neutron, any neutral hadron or a neutral electromagnetic object, which we call a photon, we do not know whether it comes from the original hard scatter or a pileup interaction. The simplest what we do everywhere is called charged hadron subtraction. That is, we remove all the particles that we can see that we know come from pileup interactions. For neutral particles, we have no vertex association, so we cannot remove it. And once we've removed it, we proceed with the jet clustering. This is what a real event looks like. It was taken in 2016. It has 80 vertices, 86 vertices. It is about, that's as bad as it gets. So one of these guys here is interesting, and 85 guys are not interesting, and all the tracks that are shown here are removed. There are ways to deal with the neutrals, but this topic is I will not discuss it. So we stop here with this image of a typical event, a typical single event with its pileup interactions. So this is the physical. This is the physical picture we make from our detector measurements after reconstruction from a given interaction. It's really hard to see anything here. Okay, let's see how we treat the statistical and systematical uncertainties in such measurements. Now, we look at this, you remove all the charged hadrons, a few particles survive. These few particles are subject to B tagging, so maybe P jets are found. The jets are clustered. There's an uncertainty from the neutral particles, and at the end of the day, we walk all the way from the detector cell to the parton momenta, hopefully reconstruct p quark momenta, top quark momenta, Higgs boson momenta, Higgs boson masses, and so on. Once we've done all that, we can begin to do analysis, and analysis is subject to uncertainties. It's worthwhile to do a little bit of groundwork, which we're doing now. You can learn that in all other areas of physics as well. I think it is a repetition. These are straightforward concepts from metrology, the science of measuring things. We should distinguish between precision and accuracy. Precision is a description of random errors. It is a measure of statistical variability. If you have low precision, your measurement scatters around a lot. Accuracy is different. It describes the systematic errors. That is, systematic difference between the true and the measured value, and that are not probabilistic. So if we have a certain true value and we measure a distribution, and our measurement follows a certain distribution, then the width of the distribution will be its precision. It will tell us how much our measurement fluctuates, and the accuracy will be the offset. The sketch shows this as well. So if we have an unbiased measurement of low precision, we are in the top right, so we get it right on average, but we have a large spread. Low accuracy, high precision means we always get the same answer, but it is wrong by a certain amount. High accuracy and high precision is, of course, what is desirable, but the amount of data limits the achievable precision, and the quality of the data limits the achievable accuracy. That was bird's eye view on systematic and statistical uncertainties. Let me discuss the two most important distributions from statistics that play the biggest role in all metrology, in particular high energy physics, cannot be done without the normal distribution. These are the Gaussian distribution. We've used it already, for example, when we calculated the instantaneous luminosity. The probability density function is given by an exponential. The normal distribution has a mean, is a location parameter typically called mu, and it has a variance, sigma squared. The square root of the variance is what we call the standard deviation. The insert here, the plot here shows the normal distribution for different values of the location parameter and the variance. A high variance means a high spread, and the location parameter gives the maximum position of the distribution. The Gaussian the normal distribution is symmetric. The standard normal distribution N01 with a location parameter at 0 and a variance of 1 is given simply by e to the minus x squared over 2. It has a cumulative distribution, which is the integral, the e to the minus x squared gives a so-called error function. It's called error function because if you try to integrate it, you end up in error. It cannot be done analytically in the sense that we cannot express the error functions with other functions. That's all it says. At the moment you call the error function a function, then it can be integrated analytically. So I don't know what analytically means in this respect. Nevertheless, the integral of the standard normal distribution is the standard error functions. It is important because we use it to define probabilities, and that's the only reason why I explain it here. Look at the standard normal distribution in this sketch here. It has a variance of 1. That means we can compute the number. We can compute the area under the. We can compute the area under the normal distribution in terms of the error function, and that informs us about how likely certain events take place depending on how far the observation is from the mean value in units of the standard deviation. I hope that was clear. If we are 1 sigma away with our measurement from the mean value, that will happen with at least 30% of the time. So if you have an expectation for a certain physics property, and you know how accurately you can measure, and you measure a shift that corresponds to your measurement uncertainty, 1 unit of your measurement uncertainty, then you should not be excited, because that will happen in 30% of the cases. If you repeat it multiple times, in 60% of the cases, you will, I'm sorry, in 70% of the cases roughly, you find a value that's closer than 1 standard model, that's 1 standard deviation, and in 30% of the cases, you find a larger number. Larger deviations are much less probable, and it falls roughly with, well, it falls with the error function, which is the integral over this negative exponential, so it falls very quickly. 2 sigma is 5%, 3 sigma is a per mil, 5 sigma is 10 to the minus 7, and 10 to the minus 7, that 5 sigma is the threshold we put on discovery. In other words, if a measurement happens under the background hypothesis, or under the standard model hypothesis, or under the null hypothesis, with a p-value with a probability of less than 10 to the minus 7, or of more than corresponding to more than 5 sigma, then we say the null hypothesis is wrong. We have discovered something else. We have discovered a deviation. One has to be very careful in formulating the null hypothesis and the signal hypothesis, but here we only discuss the probabilities. So 5 sigma means that the chances that we are wrong is in the 10 to the minus 7 regime. The number is given here. Okay, so the p-value is a statistical concept. It occurs it appears in most of our publications. It is simply the probability that our measurement, viewed as a random process, produces a result that is that many standard deviations away or further away. So it is a measure of it is a measure of the compatibility of the observed data with the null hypothesis. One important property of the Gaussian distribution is that if 2 values follow a normal distribution, let's say x1 and x2 are distributed according to the normal distribution, then their sum also follows a normal distribution. The location parameter will be the sum, and the uncertainty will be the sum squared. That's important for the proof of the so-called central limit theorem. The central limit theorem, in a colloquial sense, it tells you that if you have many effects, eventually the whole system will be described by a Gaussian under very moderate assumptions. Take, for example, an uniform distribution. Let's say that is the position of a particle between two wires of a gases detector. You have no idea where it is if you have a single measurement. So if you make a single measurement, the probability distribution will be flat. Now consider the sum of 2 such measurements, and it will become triangular. If you add more of the uniformly distributed quantities, they will approximate a Gaussian. The bottom right plot shows the sum of 6 uniformly distributed values, so it peaks at 6, and the distribution is already Gaussian. This can be proven is close to Gaussian. This can be proven rigorously if a measurement, if an observable y is the sum of observables x, then the expectation value of y will be the sum of the expectation values of x, and the variance will be the sum squared of the variances, and y will be distributed as a normal distribution, even though the variables x are distributed differently. In other words, if you add many things, what you will get is a Gaussian. This is important because our measurement uncertainties are often the sum of many independent contributions. You have a particle that goes through the detector. First, it has uncertainties from the parton shower, because we don't know exactly, if we reconstructed what the physics of the parton shower are. We only know it with some uncertainties. Now, it's certainly not the Gaussian. Our knowledge about the parton shower is certainly not the Gaussian. It's something else. It's a complicated distribution. But then there are also detector effects. There are the effects from the shower in the detector. There are reconstruction effects, threshold effects, all of which are, if you look into details, are non-Gaussian. However, because there are so many and because these effects add up, at the end of the day, the uncertainty in the momentum of a jet, for example, that I've now taken, are pretty much Gaussian, because the non-Gaussianities average out. And that's what the central limit theorem states. It is conventionally used in all reconstruction and calibration techniques throughout the detector, and it's very convenient that we only have to deal with the means and the variances and can disregard the distribution of the underlying effects, because all we need is that the many effects combine to Gaussian properties. Okay, the second distribution we have to discuss is the Poisson distribution. The Poisson distribution describes the probability of a given number of events to occur in a fixed time interval if these events occur with a known constant rate and independently of each other. For example, if you stick out your hand into the rain, assuming that the raindrops fall in an uncorrelated fashion, then the number of raindrops in the given time interval that will hit your hand are Poisson distributed. The formula is given here by the exponential. For large values, the Poisson distribution will approximate the Gaussian, also because of the central limit theorem. It's interesting that it's important that while the expectation value for large values of lambda, the variance is the same as the expectation value. In other words, the standard deviation, the uncertainty, is the square root of the mean parameter. So here we see for lambda, the Poisson distribution for lambda equal 1, which means we expect one event per time interval. It is highly non-Gaussian. It's unsymmetric. It is not defined below 0 because you cannot have negative counts. So it is highly non-symmetric. For lambda equal 4, which is the probabilistic distribution if we expect a rate of on average 4 events, is already Gaussian. It already resembles a Gaussian, but has a higher tail to high values. For 10, it almost looks like a Gaussian with a location parameter of 10 and a width of square root of 10. So that's roughly 3, a little bit more than 3. So this is the Poisson distribution. Examples for the Poisson distribution are, well, if you see a hand into the rain and you count the number of drops that hit you at a given time interval, the clicks of a Geiger counter in a given time interval are also Poisson distributed. Now, not necessarily so. If the time interval is too large, then the dead time of the Geiger counter makes the count rate non-Poissonian, because if the detector has a large dead time, then it will be less efficient in case it has many hits, because then the dead time is important. So all these statements, of course, come with a certain number of caveats. The number of Prussian cavalrymen killed by horse kicks. That was how the Poisson distribution was discovered, because a Prussian cavalryman, they were trained the same way, and the horses were standardized, and hence the rate of cavalrymen being killed by horses was a constant over the whole Prussian army, and was the subject of the first probabilistic study leading to the Poisson distribution. The number of particle interactions of a certain type produced in a given time interval or for a given integrated luminosity is also Poisson distributed. We've calculated that at the LHC around 100 C bosons are produced each second. The rate of C bosons is roughly 100 per second. So now you know that you can expect 100 C bosons plus minus 10 in a distribution that's almost Gaussian, but in truth is Poissonian. You will not see the non-Poissonian tail for this large number, but if we talk about the Higgs boson has a rate of 0.1 per second inclusively. This is a highly non-symmetric distribution. Okay, that was what I wanted to say about the normal and the Poisson distribution. Let's look now at uncertainties. I put here an example of statistical and systematical uncertainties and how we quote them, and we usually quote them separately. So we say a value x has a certain number, 2.3, but because we're physicists, we always wonder about the uncertainty in a quantity. I put here 0.05 as a statistical uncertainty and 0.025 as a systematical uncertainty. It's just an example. So the statistical uncertainties are random. They can be reliably estimated by repeating the measurement and simply looking again with uncorrelated data. They follow a known distribution. Typically at high energy physics measurement, they follow a Poissonian distribution. In 1 second, you observe 100 C bosons. In the next one, you observe 105, and in the one after, you observe 95 C bosons. And that's completely fine, because square root of 100 is 10, and 10 is 1 sigma of the Gaussian that approximates the Poissonian in this case, so you're completely fine. If in the next second you observe 3 C bosons, you know that your detector is broken, just from the statistical uncertainty. Detector is broken means you have a large unaccounted for systematic effect. It cannot be statistical. So statistical uncertainties follow a known distribution. They can be measured by repetition. Because of this property that the variance is the same as the mean, and so the uncertainty, which is the square root of the variance, is the square root of the mean, the relative uncertainty reduces with 1 over square root of n, where n is the sample size or the number of events measured, or it can be, so n is proportional to the amount of data that you have, so to the amount of luminosity. In many high energy physics use cases, one expects a certain Poissonian mean number of events. Let's say you expect 2.3 events, like is given here, and then one observes an integer count. You either observe 2 or you observe 3 or you observe 10. The expected measurement error, the statistical uncertainty, is then square root of the expected number. So you expect 100 Z bosons in a given time interval, and your expected uncertainty is 10. Systematic uncertainties are different. Systematic uncertainties cannot be calculated from repeating a measurement or from sampling the fluctuations, which amount to repeated measurements. In most cases, the systematics do not reduce as 1 over square root of n. Think about the non-compensating calorimetry. We have an uncertainty in the measurement of the energy that's proportional to the response difference of the electromagnetic and the hadronic calorimetry response. It was constant with energy. So whatever you do, you cannot tell better than a certain constant for some measurements. For example, the calorimetry measurement of an energy. However, systematic uncertainties can reduce with more data, because more data allows better auxiliary measurements. If you have 10 times more the data, you can do better control region studies, and you can intrinsically calibrate your detector with better accuracy, and that leads to a reduction on systematic uncertainties. However, you have to invest, you have to make analysis, you have to do measurements, you have to have a better understanding of what's happening in your detector. This is a non-statistical process. This is a scientific process. You understand better the features of your detector. In general, the systematic uncertainties are much more difficult to determine than the statistical ones. Statistical one is just square root of n, or square root of whatever the stochastics is in your process. Systematics, you have to understand what's going on. In high energy physics experiments, as I know Lucas will confirm, 90% of the work goes into assessing the systematic uncertainties in various ways. Systematic uncertainties are not mistakes. A mistake is a mistake. A mistake is something that you fix. A systematic uncertainty is a lack of knowledge that leads to an uncertainty in your measurement. So a systematic uncertainty is some lack of knowledge that you may or may not be able to improve, but at the end of the day, you have a lack of knowledge on your response in your calorimetry and other features, so that the calibration can never be perfect, will always be subject to uncertainties. If you make a mistake, then that's something else, and that's what you can fix. We typically quote statistical and systematical uncertainties separately, because they give us an idea whether taking data would be more helpful. Let's go back to our example here. 2.3 plus minus 0.05 plus minus 0.02. 0.05 is the statistical uncertainty. It's twice as large as the systematic. We say that this measurement is statistically limited. If I take a student, which I sometimes do, and let them work on the systematical uncertainties and improve by a factor of 2, it will not help, because then we have 2% uncertainty on the systematic, 5% from the statistic, and if this 2% reduce to 1, we still have the 5. So it doesn't help. That's why we say this measurement here is statistically limited. We need more data we can improve the total uncertainty by adding more data. How much data do we need? Let's take a factor of 4. A factor of 4 means that if this is an event count or something that derives from an event count, the statistical uncertainty will reduce by a factor of 1 over square root of 4. Square root of 4 is 2, so it will reduce by a factor of will reduce by a factor of 2. That means the statistical uncertainty will then be 0.025. It will be equal. If we take 100 times more data, then 1 over square root of 100 is 1 over 10. If we take 100 times more data, the ensuing statistical uncertainty will be 0.005 with an extra 0 here. At this point, the systematic uncertainty is dominating because it's 5 times larger than 0.005. Then it does not help to take more data anymore. At this point, if you have that much data, you should work on the systematic uncertainty. We call these measurements systematically limited. During operation of an experiment, the data gradually increases. When we started 10 years ago, the data increased exponentially roughly. We would double our data set every 2 or 3 weeks. So it did not really pay off to work on, it was not very important to work on systematics. They had a certain value, but the statistical uncertainties were large. We had not yet taken a lot of data. These were the first events. We could watch the statistical uncertainty reduce. And then more and more measurements entered the systematic regime, which is when they become systematically dominated. In the beginning, with the first few events, the rediscovery of the top quark was a statistically limited process. We didn't exactly know whether, well, we had a few hundred top quarks. With 100 top quarks, you get a 10% uncertainty. Now we have hundreds of millions of top quarks, and many measurements with the top quarks and with other, with the Higgs boson, are no longer statistically limited. We have so many events that the systematic effects contribute dominantly to the total uncertainty. Okay. Let's look at typical Hadron Collider systematics. This is again an overview in a different terms. So we have our initial protons or protons and antiprotons. At the LHC is proton and proton. Protons and the protons contain quarks and gluons. In the rest, in the lab frame, because of Lorentz contraction, these are actually tiny disks that collide somewhere in the detector. Then our complicated event takes place and gluons and quarks are ejected. They form hadrons. The length scale of hadron formation is still 10 to the minus 15 meters, so it's essentially at the detector. I'm sorry, at the interaction point. Then the tracks and the charged and neutral particles travel through the detector, which is at the meter scale, make hits in the tracking, in the electromagnetic and in the hadronic system, and are reconstructed. So the physical evolution evidently goes bottom up here. It starts at the interaction, at the primary collision, and moves outwards towards the detector, where the physicist waits and records the signal. The work of the physicist is then to combine these measurements and to work his way back down to where the initial collision has happened. At the lowest, at the first stages here, we have uncertainties from the theoretical description of the hadronization, and we have uncertainties from the parton distribution functions. We do know that the up quark and the down quark PDF peak at roughly a third, which means that it's frequent that we observe a quark inside the proton that carries around a third of the momentum of the proton. That's because a proton can be thought of as a bound state of 3 quarks and with a field of gluons, held together by a field of gluons. But we do not know the parton distribution functions with infinite precision. As we've discussed at length, they need to be measured. Only their momentum transfer dependence, the q-squared dependence, the scale dependence, that's what can be computed. The dependence on x cannot be computed. It has to be measured, and there are only finite number of measurements, and hence there's an uncertainty. In particular, the high X gluon PDF has very large uncertainties. It goes through the roof for high values of X. So these are the theoretical uncertainties. One always has to vary the parton distribution functions and see how the measurement result would change. Then there's the large number of reconstruction and calibration uncertainties. That pertains both to the jet and to the lepton system. You can imagine that the reconstruction of tracking, electromagnetic, and hadronic effects is subject to the details of the showering of these particles in the subdetectors. If there is a dead cell here, and you don't know that there is a dead cell here, you have a systematic effect because your energy reconstructed for jets pointing in this direction will be slightly lower. The detector alignment is, of course, crucial for event reconstruction. That means the relative position of the hits in the tracker and the calorimetry must be known with high accuracy. However, they will be dependent on the B field because the detector moves if the B field changes, and hence it becomes B field and time dependent. Electrons show a shower in the electromagnetic calorimetry. Electrons can, however, be created by photons that are showered in the tracker. So a typical systematic uncertainty applying to final states with electrons is the rate of photons converting into electrons. You don't know how often that happens. It happens with a certain rate, but that rate is not very well known, and hence the probability of falsely reconstructed events where you think you have an electron, but really you have a photon, is subject to an uncertainty. Then we have jets. Jets are the clusters that the output of the clustering algorithm from the jet from the jet clustering algorithms executed on the particles. We know that these jets have a certain contribution from pileup. Even though we remove all the charged particles from the pileup vertices, there's still the neutrals, the neutrons, the photons, and so on. And there's no way of knowing which particle is which in the absence of a track. So there is a fluctuation in the jet energy coming from the pileup activity. It can be subtracted, but it can only be subtracted on average. That means if you have 40 pileup, you know that on average, okay, each jet gets 5 GeV from that 40 pileup, so I remove these. But you don't know whether you don't know jet by jet whether it was really 5 GeV, because this number fluctuates according to a distribution that's approximately Gaussian. So that also causes systematic uncertainties. And then there are low-level effects in the detector. We collect for example, an ionization signal. In many detectors, we collect an ionization signals measured in femtocoulomb because it's charge carriers that we collect. Those are calibrated to GeV units with conversion factors that are measured individually for each detector cell. So we know what a femtocoulomb in each cell means in terms of GeV. But these maps are far from perfect. The detectors age, they shield each other, they guide the showering formation. So that is a stochastic, there are systematic effects that pertain to these conversion factors, and they are large, can be large, and play an important role. Then the timing of the hit is important. Whether a certain hit belongs to the ongoing or the previous bunch crossing. You may have a hit here that has a timing that's in between the previous bunch or this bunch. So you're not sure whether this time the timing measurement didn't work and the hit belongs to that jet, or whether actually it belongs to the previous bunch crossing and belongs to a completely different particle happening, showering at a different time. And sometimes you're not even sure whether you had a physical hit from a particle hitting the detector, or whether that was electronic noise or a stray particle or a cosmic or some other effect that's not accounted for in the simulation. So all these effects are typical, the bread and butter work of the high energy physicist as he walks his way from the reconstructed objects all the way down to the primary collision that we're interested in. Good. That was what I wanted to say about event reconstruction and uncertainties. I stop the recording.